How FPT and optimization problems relate. In this section, we demonstrate an interesting relationship between fixed parameter, tractability, and approximability of NP optimization problems. In particular, we will show the fixed parameter tractability for some well-known NP optimization classes and investigate the approximability of NP optimization problems based on their fixed parameter tractability. We remark that this has more than passing interest. Aside from the original work in Gary and Johnson, there have been few advances which enable one to prove that an approximation problem has no good approximation algorithm, even assuming P is not equal to NP. The exception to this is the recent work of Aurora et al., when demonstrated that many NP optimization problems do not have good approximation algorithms unless P not equals to NP. We shall show that in many cases the fixed parameter intractability of an NP optimization problem implies a non-approximability of the problem. This result applies to many problems and not covered by the Aurora et al. Results. Thus, the study of fixed parameter complexity provides a new and potentially powerful approach to proving non-approximability of NP optimization problems. Our concern will be parameterized problems associated with optimization problems. To this end, for a relation R from greater than or less than equals to, for example, we can associate a natural decision problem. Decision problem associated with the NP optimization problem Q equals to the tuple IQ, SQ, FQ, opt-Q. Input X and IQ. Parameter a positive integer K. Question: does R of OPT Q of X, K hold? We write QR for the decision problem associated with R, the complexity of the parameterized problems. Q equal, Q less than equals to, and Q greater than equals to have been studied in the literature. For example, Leggett and Moore showed that for many NP optimization problems, Q, the problems Q less than or equals to, and Q greater than or equals to, are in an NP union co-NP, whereas the problem Q equal is not in NP union co-NP unless NP equals to co-NP. With the following elementary argument, Lyman, Kai, and Chain demonstrate that the problems Q equal, Q less than equals to, and Q greater than equals to have the same complexity from the viewpoint of a fixed parameter tractability. Lemma 4.2, Kai and Chain. Let Q be an arbitrary NP optimization problem, then the three parameterized problems Q equal, Q less than or equal to, Q greater than or equal to, are either all strongly, uniformly fixed parameter tractable or all strongly, uniformly fixed parameter intractable. Proof: we argue for uniformly FPT. The other arguments are similar. Suppose that the parameterized problem Q less than or equals to is fixed parameter tractable. Thus, there is an algorithm A less than equals to that solves the problem Q less than equals to in time big O of f of k times n to the c, where f is a function and c is a constant independent of the parameter k. To show that the parameterized problem Q equal is fixed parameter tractable, note that the condition k equals to OPT Q of X is equivalent to the condition k which is less than or equals to OPT q of x, and k plus 1 is greater than OPT q of x. Therefore, given an instance xk for the parameterized problem q equal, we can run the algorithm a less than or equals to on the input xk and on the input xk plus 1 to decide whether k is equals to OPT q of x. The total running time is obviously bounded by big O of f of k plus f of k plus 1 and the results of the summation of two f functions times by n to the c. Thus, the problem q equals 2 is fixed parameter tractable. Conversely, suppose that the problem q equals 2 is a fixed parameter tractable. Then there is an algorithm a equals 2 that solves the problem q equals 2 in time big O of f prime of k times n to the c prime, where f prime is a recursive function and the c prime is a constant, independent of the parameter k. Now, given an instance xk of the parameterized problem q less than or equals 2, we run the algorithm a equals 2 on k inputs x0, x1, x2, and so on until xk minus 1. It is easy to see that xk is a no instance of the parameterized problem q less than or equals 2, if and only if the algorithm a equals 2 concludes yes for at least one of those k inputs. Note that the running time of the above process is bounded by big O of k times f prime of k times n to the c prime. Thus, the problem q less than or equals 2 is a fixed parameter tractable. Therefore, the parameterized problem q equals is a fixed parameter tractable, if and only if the parameterized problem q less than or equals 2 is fixed parameter tractable. In a similar way, we can show that the parameterized problem q greater than or equals 2 is fixed parameter tractable, if and only if the parameterized problem q equals 2 is fixed parameter tractable. The key result tying FPT with approximability is the following theorem, which extends earlier work of Lyman-Kai on pseudo-polynomial time and FPT. Theorem 4.3. If an NP optimization problem has a fully polynomial time approximation scheme, then it is a fixed parameter tractable. Proof. Suppose that an NP optimization problem Q equals to the tuple IQ, SQ, FQ, OPTQ has a fully polynomial time approximation scheme A. Then the algorithm A takes as an input both an instance x in IQ of Q and an accuracy requirement epsilon greater than 0, and then outputs a feasible solution in time big O of P of 1 over epsilon and the size of x, such that the relative error R A of x is bounded by epsilon, where P is a two-variable polynomial. First, we assume that Q is a maximization problem. By lemma 4.2, we only need to show that the problem Q less than or equals to is fixed parameter tractable. Given an instance xk, for the parameterized problem Q less than or equals to, we run the algorithm A on input x and 1 over 2k. In time big O of P of 2k and the size of x, the algorithm A produces a feasible solution y in S q of x such that our a of x is equals to OPT q of x minus fq of xy over fq of xy, which is less than or equals to 1 over 2k, which is less than 1 over k. If k is less than or equals to fq of xy, then certainly k is less than or equals to OPT q of x, since q is maximization problem. On the other hand, if k is greater than fq of xy, then k minus 1 is greater than or equals to fq of xy. Combining this with the inequality, OPT q of x minus fq of xy over fq of xy, which is less than 1 over k, we get k is greater than OPT q of x immediately. Therefore, k is less than or equals to OPT q of x if and only if k is less than or equals to fq of xy. Since the feasible solution y can be constructed by the algorithm A in time O of p of 2k and the size of x, we conclude that the NP optimization problem Q is fixed parameter tractable. The case when Q is a minimization problem can be proved similarly by showing that the problem Q greater than or equals to is fixed parameter tractable. Actually, the proof above demonstrates that any optimization problem with a polynomial time approximation algorithm A of x epsilon with the additional property that there exists a constant c independent of epsilon such that A of x epsilon runs in time big O of the size of x to the c for a fixed epsilon is fixed parameter tractable. We remark that theorem 4.3 allows us to establish that many problems are FPT. For instance, bounded knapsack below is FPT. Bounded knapsack. Input U, which is a subset equals to n with sizes S of A in Z for A in U and B, which is less than or equals to K. Parameter, a positive integer K. Question, is there some S which is a subset equals to U with the summations of S of A summing for all A in S, which is equals to B. This follows by the algorithm of Ibarra and Kim, similarly from the approximation algorithm of Lipton and Tarjan, shows that the problem planar independent set below is FPT. Planar independent set. Input, a planar graph G. Parameter, a positive integer K. Question, does G have an independent set of size K? Here, a set S of vertices of G is called an independent set if and only if for all x, y in S, xy is not an edge of G. A final example by the randomized fully polynomial time approximation scheme of Brightwell and Winkler. The following problem is randomized FPT with the obvious meaning. Linear extension count. Input, a partially ordered set P. Parameter, a positive integer K. Question, does P have at least K linear extensions? A linear extension L of a poset, the set of A1, A2, A3 until AN less than or equals to is a linear ordering, the set of A1, A2, A3 until AN less than or equals to star, such that if AI is less than or equals to AJ in P, then AI is less than or equals to star AJ in L. The problem of counting linear extension is shown in Brightwell and Winkler to be sharp P complete. Theorem 4.3 implies many other natural problems are FPT. One powerful application comes from the contrapositive. Corollary 4.4 Chi and chain. If an NP optimization problem is fixed parameter intractable, then it has no fully polynomial time approximation scheme. In particular, under the current working hypothesis that W1 is not equal to FPT of Chapter 10, the NP optimization problems that are W1 hard under the uniform reduction have no fully polynomial time approximation scheme. Following Lyman, Chi, and chain, we remark that corollary 4.4 complements a classical result of Gary and Johnson, theorem 6.8, that a strongly NP-hard optimization problem Q with OPT Q of X less than P of the size of X, num of X, for some two-variable polynomial P has no fully polynomial time approximation scheme unless P equals to NP, where num of X is the largest integer appearing in the input instance X. The consequence W1 equals to FPT in corollary 4.4 is weaker than P equals to NP, but the assumption in corollary 4.4 requires neither strong NP hardness nor the condition OPT Q of X is less than P of the size of X and NUM num of X. There are a number of applications of theorem 4.3. One not covered by the classical literature is that of the so-called VC dimension from the computational learning theory has been studied extensively in the literature. As we see in chapter 11, the VC dimension is W1 hard, and so cannot have a fully polynomial time approximation scheme unless W1 is equal to FPT. However, Papadimitriou and Yannakakis have shown strong evidence that this problem is in NP, but neither NP nor NP complete. Therefore, theorem 6.8 of Gary and Johnson is not applicable. The conclusion is that the VC dimension is unlikely to have a fully polynomial time approximation scheme, even though it seems easier than NP complete problems. By making a natural distinction between different kinds of polynomial time approximation schemes, an even stronger connection between fixed parameter intractability and non-approximability can be established. Consider the following results. For the problem Euclidean traveling salesman, there is a p-task due to aurora that runs in time big O of n to the 30 over epsilon, where n is the size of the graph. For the problem maximum independent set for planar graphs, where there is a p-task due to Baker that runs in time of big O of f of 1 over epsilon times n. What we can notice about the above examples is that the running times for an approximate solution within factor of 1 plus epsilon of optimal are for fixed epsilon bounded by a polynomial, but in the first case the degree of the polynomial is a function of epsilon, whereas in the second case the exponent of the polynomial is independent of epsilon. This is precisely the central issue in parameterized complexity, so it is natural to make the following definition. Due first to Baskian. Definition 4.5. An approximation algorithm for an optimization problem is an efficient p-task if it computes a solution with a factor on 1 plus epsilon of optimal in time big O of f of epsilon times n to the c for some function f and some constant c. Baskian was the first to prove the following important theorem which has subsequently been independently rediscovered by several others. Theorem 4.6. If an NP optimization problem is fixed parameter intractable, then it has no efficient p-terms, unless FPT equals to W1. The theorem is proved by essentially the same argument as for theorem 4.3. Boscan's theorem provides a very good connection between parametric intractability and non-approximability.